So far, we've looked at the architecture of encoder and decoder. And just to quickly recap, so an encoder takes in the tokenized text and it creates embedding out of it. And there is an attention layer over here, which just basically assigns weight to all these embeddings. And then there is a fully connected neural network. And this also goes into the decoder as well. And within the decoder, we obviously have the input text again, but then we are also receiving this data from encoder. And this is really helpful in tasks like summarization, where you need additional context from the input, or like translation, where again, you need more context here. And then we have the same thing where there is an attention layer to get the weights, and here again, and there is a neural network and then another fully connected layer at the end. So that's a quick summary of encoder and decoder. Now, there are scenarios where you might not even end up using both of these together based on the application. So there are a few types of transformers. So there are encoder only, encoder decoder, and of course decoder only, right? So we are going to look at these three things in this section. And again, to reiterate and go back to the project life cycle itself. So whenever you're working on these LLM projects, there's of course the scope, the use case of what you're trying to build, and then you select a pre-trained model over here. And this is where we are, where you have to choose if you want to use an encoder only or decoder only or encoder decoder based on your application. And then we continue on with building whatever we want to do next, like prompt engineering or fine tuning or do RLHF, human feedback, etc., etc. So again, a base for this is understanding the kind of transformers there are available for us. So let's talk about encoder only over here. And encoder only models are, there are a few of these over here. There's BERT, Roberta, DistilBERT, and so on. And these became really famous in some of these tasks like sentiment classification or analyzing the sentiment of a sentence, and named entity recognition, like you give it a sentence and you want to pick out the name of the person, the place, or an organization. And there's obviously question answering, mass language model, and several other applications where you just only need encoder only model. And here's an example of this, right? How this works internally. So imagine this is our original text. The teacher teaches the student. And once we have this input, this actually goes through and gets this masked language modeling, where we call it MLM. And then we have the teacher, and then there is a blank over here, and then the student. So we are removing the teachers. And this is how this model gets trained, where we create a blank, and it's like fill in the blanks. And the objective of this model is to reconstruct the text or denoise it and then come up with a sentence. So we know what we're starting with, but we don't provide this as input. We just give this as input to the model, and its job is to fill in this blank, and it usually looks at this bidirectionally from either direction of these two words, and then predicts this word over here called teachers, right? So we are working with objective reconstructing text in encoder only situation. So that is encoder only. Now there is decoder only, and here we have all the chat GPTs, the GPT-3, GPT-2, Neo, and so on. And these are like auto-regressive models. And here are some of the tasks like text generation, causal language modeling, etc. And how does this work internally? So again, let's think we have the same text. The teacher teaches the student. So here we use something called as causal learning modeling, whereas in encoder only we were doing masked language modeling. So here we just start the sentence off with the two words, and the modeled job is to predict the rest of the words over here. And here, like we said, the objective is to predict the next token. And here we are just having the unidirectional context. So in comparison to this bidirectional context in MLM, with causal modeling, we are only giving it the unidirectional context, and its job is to predict the next word. And even in ChatGPT kind of fails in certain applications where you want it to look at the bidirectional context, because it's only predicting the next word, so it can't go back and predict the previous word, right? So that is decoder only. And then of course we have the encoder and decoder model over here, which is sequence to sequence models. And here we have BART, T5, translation models, and so on. So good example are translation, summarization, generative question and answering, and etc. So here, let's imagine we have the same text, the teacher teaches the student. And here it works on the span corruption, where we again give the teacher and a few blanks over here on the student. And its job is to fill in this sentinel token, which is called a sentinel token because its objective is to reconstruct this span over here. So that is what we have within these different types of models or different types of transformers. There's encoder only, encoder decoder, and decoder only. And our job is based on our scope and use case we're trying to build is to use one of these models. And of course, finally, you also have this shot of summary text over here where we have the original text, and with on-row encoding, which is also MLM encoder only, we give it a mask over here. With the autoregressive, we just give it text, and then it's allowing it to predict the next token, which is decoder only, like ChatGPT, etc. And then the sequence to sequence is span corruption, and its job is to again fill in this blank over here, which is decoder encoder architecture, right? So this is all about the different types of transformers. I think we've had enough of introduction to all these things. In the next section, we look at running a few pieces of code and try to understand how we can run this in Python.